This is chapter 11.2, Calculus with Parametric Equations. But before we do that, there's another formula you need to know, and it's the length of a curve of a regular function. So if you have a function y equals f of x, how do you find the length of the curve, this red curve right here? How long is that? How do you do that? Well, that's what this lesson is about. So we are going to approximate the length of this curve by doing a bunch of triangles, basically Pythagorean Theorem, multiple times. So if I were to make a triangle here, I think you would agree this hypotenuse is approximately the length of that piece. We're going to do it again here. And again, this approximates that. And we're going to do another one. Where this approximates this. And we can keep going. I'm just going to do one more just to get the point across. So if I were to add this length plus that length plus that length plus that length, that's a rough approximation of my arc length. So that's the concept we're going to build on. Now I claim this is delta x and this is delta y. I think you agree with that. Now from that, we can actually find the length of the hypotenuse because that is a right triangle. And maybe you might see where we're going, maybe you won't. But let's do that. We're going to use Pythagorean Theorem, and we're going to find the length of that piece, the hypotenuse. So let's do that. Let me call it, let's see, we'll call it L. I guess L will work. We'll call this side L. And L squared is delta x squared plus delta y squared. So L will be the square root of delta x squared plus delta y squared. Not bad, eh? But we need to add up all these L's up. So I'll call this L sub k. And if I add them all up, I'm going to add up my L sub k's from the first one to the last one, which will be, and I guess, how do I do this? Delta x sub k squared plus delta y sub k squared. I guess that would work. So that's an approximate area with n triangles. Well, I can continue increasing the number of triangles, right? I think I can. But the more triangles we have, hopefully you see, the more accurate it's going to be. Because if I take a smaller triangle, let me do what color? Green? If I do 2 triangles here, you see it's more accurate. And the more triangles I have, the error approaches 0. So we're going to do this. If you take the limit as n goes to infinity of this, that would be the actual arc length. We'll call it L for the length of the arc. Interesting. We're going to do some side work here where I don't have room. Let me do it over here. If I take delta x squared plus delta y squared and factor out a delta x squared, what's left? 1 plus delta y squared over delta x squared, right? So that's what I'm going to do. I'm going to replace this with delta x squared 1 plus delta y squared over delta x squared. then I can factor that out, right? Square root of squared is just 1. And so I'll get this. And some of you may see where we're going with this. Now I should have x sub k's here. I apologize for not having my x sub k's. So what I'm going to get is square root of 1 plus delta y sub k squared delta x sub k squared times delta x sub k. Well, remember when we did derivatives? This is a big change in x. But when we took the limit as n, or as k goes to infinity, when we did the derivative, definition of derivative, or we had a couple versions of it, x approached a, or h approaches 0. But basically, in the derivative, we let the distance between the points approach 0. Well, as n goes to infinity, the number of triangles, delta x is going to approach 0. But when it did that in derivatives, it became dx and dy. So what's going to happen to this, our arc length, basically by taking this limit, these will become derivatives. And summing is your integrating. When you add up a bunch of things, you're integrating. So I'm going to do this. This will be square root of 1 plus. Now dy dx is derivative when your delta x approaches 0. So this is derivative. So that's going to be dy dx squared. And again, as dx approaches 0, or delta x approaches 0, that becomes dx. And this is the formula that you have to know. That is your formula for the length of an arc. Or you can write it like this. Okay, you could either memorize that or understand where it comes from, but that is the formula for the length of an arc. All right, so here it is, given formally, and we're going to do an example. You can do this if you want to, but if you want to, you can pause. All right, welcome back. I forgot to mention A and B on this. A would be the starting point, A, and B would be your ending point. So it's your starting x and ending x values. And we know we're working with x's because of the dx. So let's do this. We're starting at 0, ending at 4. That's my A and B. I can do that. And square root of 1 plus. Now I need to find the derivative of f. So the power rule, I bring the 3 halves in front and decrease the power by 1, and I get 1/2. So I'm going to have 3 over 2 square root of x squared, because this says square it, and it's with respect to x. Now we're on something. We're on a path. We're on a way to the answer. That's going to be 9x over 4 dx. When you square that, you get 9/4. Square root of square of a square root is x. All right. This looks like a u sub to me. I can't integrate this because this is an x. If that were x, that'd be easy. But since that's not x and it's a function, this is u sub. Du would be 9/4 dx. And so I have the dx, but I don't have the 9/4. How do I get that there? Well, now I do. So 4/9 times 9/4 is 1, so I haven't changed anything. Now we're ready to do this. So we have the 4/9. This box is u, so it's u. 9 over 4 dx is du, So I'm going to put du there. And we need to change the limits of our integration. When x is 0, u is 1. So that's got to be 1. When x is 4, we're going to have 1 plus 9. We're going to have 10 here. So why do we need to change these? Because this tells us our variable is x. So that's our starting x and ending x. We have changed our variables to u's. So this needs to be a u and that needs to be a u. So we plug in the x to find the new u. We plug in this x to find the new u. So we get that. Well, this is u to the 1/2. The antiderivative of u to the 1/2, I add 1 to the exponent and divide by that. And that's going to be from 1 to 10. I'm almost done. I multiply by the reciprocal of that. So I have 4/9 times 2/3, u to the 3/2 from 1 to 10. All right, this will be, continuing on, 8 over 27, u square root of u cubed. I'm just going to rewrite it like that, which is 8 over 27 square root of 10 cubed minus 8 over 27 square root of 1, actually cube root of 1. No, square root of 1 cubed. Wow, brain is not working well. And then to simplify this, well, 2 of these make 10, but we're cubing it, there's 1 left. So it's going to be 80 radical 10 over 27 minus 8 over 27. So here's my answer, 8 radical 10 minus 8 over 27. You can factor that, factor out an 8, it's 10 radical 10 minus 1 over 27. Now, in all actuality, you could have stopped right there. You didn't have to go further. But that is how you find arc length using that formula. All right. Hopefully I didn't make a mistake. There's always a chance I made a mistake. But such is life. Okay, let's move on to parametric equations. So that's with our old standard equation. Now let me clear this page off because it's not so pretty. Okay. So now we have a parametric curve. How are we going to find the arc length of a parametric? Well, it's going to be the same process that we did for the regular function, but now we have parametrics, and it's actually easier. When you see this, you're going to be like, duh, makes total sense. It's the same thing. So here we go. Again, we're going to make triangles. And what's cool, these triangles approximate, that was bad. Try that again. These triangles approximate the length of, trying to do two things at once. It's not working well. Approximate the length of, I can't even think straight. The length of the arc. So I'll call this L1, L2, L3, L4, L5. If I add those up, I get the arc length. Well, let's figure out how to do that. So we're going to sum all of our L's, but let's do this. This is delta x sub 1, delta y sub 1, and you have delta x sub 2, this will be delta y sub 2, and so on and so forth. So we use the Pythagorean theorem to find L1. Pythagorean theorem says delta x1 squared plus delta y1 squared. And then you keep on changing for each successive triangle. So I'm going to put a plus dot 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 till you get to your last triangle. But then here's where it gets cool. What we're going to do next, we're going to do something. Oh, I know what it is. Let's think about what's going on here. These are parametrics. Delta x, delta y. Let's change this. So our L sub k, oh, I know what I messed up on. I need that. So we're going to go from k equal 1 to our last one, and it's going to be this, delta x sub k squared plus delta y sub k squared. All right, we're looking good so far. All right, what are we gonna do? This is L. So I want the exact value, right? These are approximates. The reason they're approximates because we have error. That's not the same as a curve. That's not the same as a curve. But if we make the number of these triangles approach infinity, we're going to get the exact length of the curve. So L is the limit as n goes to infinity of this sum All right, so we're getting closer to what we want. But this, remember, x and y are defined differently. They're separate. So conceptually, if n goes to infinity, then these approach 0 and they become derivatives in a sense, the small change in x. And adding, remember when we integrate, it's a way of adding a lot of small things. So this will change to integration. And we're going to have a starting t and ending t. So I'll still call it a and b. But this is going to become dx squared and dy squared. Well, what's dx and dy? Well, it's the derivative of x and the derivative of y because x and y are separate and they're in terms of a third variable t. So it actually becomes this, dx dt squared, dy dt squared. Now, I took some liberties there. I didn't fully explain all the little details, but you get the picture. It's going to be change in x, change in y. But change in x, when it gets really small, is the derivative of x, which is dx dt. Change in y is derivative of y, which is dy dt. So that is our formula for the arc length of parametric curves. And here we have it right here. So you just have to know these formulas. It's delta x squared plus delta y squared. Delta x squared plus delta y squared, square root, Pythagorean theorem. Delta x squared plus delta y squared, square root, Pythagorean theorem. And when you integrate, you're adding up all those little short segments of the Pythagorean theorem. And that is how you do parametric. So you have to know the distinction between this formula here. Wow, this should have come lower. This should have been down here, and that should have been part of the definition. I messed up on that. But it's just 1 plus the derivative squared, square root, and integrate. But when you have parametrics, a separate x and y coordinate, then you do the derivative of the x, derivative of the y, you square those in square root of Pythagorean, and you add them up by integrating. So all of these are different forms of arc length. So we have an example here that we're going to do. How do you find the arc length of this shape? If you were to graph this function parametrically, you get this. So we're going to add all 4 of those little arches to get our answer. So we're going to go from, but actually if you think about it, okay, our angles, or our times, we're going to start at 0, and then at this point it's pi over 2. How do I know that? Because the sine of pi over 2 is the y coordinate, it's the largest at pi over 2. And so that's why that's going to be pi over 2. 0 to pi over 2 is going to go from there to there. This is going to be up to pi. That's 3 pi over 2. That's 2 pi. So what we're going to do, we're just going to find one of these and multiply by 4. So we're going to go 4, 0 to pi over 2, and we're going to use the formula. X prime of t squared plus y prime of t squared. Well, what's x prime? We need to take the derivative. I need to move this lower. I just shoved it too close. So this is box cubed. The derivative of box cubed is 3 box squared times the derivative box, but derivative cosine is minus sine. And then y prime, same thing. We have box cubed. So the derivative is 3 box squared times the derivative box, but derivative sine is cosine t. And we're going to plug that in to this formula. So we're going to have minus 3 cosine squared sine. Minus 3 cosine squared sine. And for the second one, and that's all squared, by the way, bro. And then for the second one, we're going to have 3 sine squared t cosine t squared. And we're going to do some fun stuff with this. So at this point, let's square those. Negative 3 squared is 9. Cos squared squared is a 4th power. Sine squared will be 2nd power. We're going to square this. It's going to be 9. Sine squared squared is going to be sine to the 4th. And cosine squared is cosine squared. So now we get that. Now we're going to factor. Do they have anything in common? And they do. Let's see what they have in common. Let me highlight this for you. They both have a sine squared, right? So I'm going to take sine squared out. And they both have cosine squared. So I'm going to take cosine squared. And they both have a 9. I'm going to take the 9 out. So I'm going to take out 9 cosine squared sine squared. And what's left over? Well, if I take the 9 out, I take 2 of those out, and all of that out, I'm left with cosine squared. And if I take the 9 out, and I take the cosine squared out, and 2 of the sines, I'm left with sine squared. And lo and behold, magic starts to happen. What's cosine squared plus sine squared? That's 1. That's 1. That's uno. Wow, this is beautiful. Well, we have the square root of 9, cos squared, sine squared, right? dt. I forgot my dt on all these. dt. That's my duty to remember that. That was lame. All right, but the square root of 9, we know the square root. The square root of that's 3. Square root of those, the squares disappear. And it gets more beautiful as we go. It's going to be 3. I'll pull the 3 out in front. And we're left with cos t sine t dt. Oh no, boo-hoo, I'm in trouble. Because what's the antiderivative of this? It's going to be a u sub again. I'm going to make u, I'm going to do a different color. U will be sine t, du would be cosine t dt. But what's cool, we already have cosine t dt right there. And then this will be u, so I can rewrite all this as 12 integral u du. See, there's u, there's du, but we need to change the limits of our integration. So when t is 0, sine of 0 is 0, u is 0. When t is pi over 2, sine of pi over 2 is 1, so we're going to go to 1. We're almost there. Take the antiderivative, that'll be u squared over 2 from 0 to 1. Plug in 1. Then plug in 0. Well, that's going to be 0. So our answer is going to be, what is that? Is that a 1 squared? I think, yeah, it's a 1 squared. So that's going to be 6. The answer is 6. That's my answer, and I'm sticking to it. That was crazy, but I think the algebra and the trig was hard on that, but the actual math part of it, the calculus, that wasn't so bad. All right. So this will be the next topic for the section, Theorem 11.1, derivatives for parametric curves. So you have a parametric equation defined with x and y with your parameter t. Now, if you want to find dy dx, it's going to be dy dt divided by dx dt. Now, let me show you why. If you change this and multiply by the reciprocal, you're going to flip that to make it dt dx, and through the chain rule, you'll see that gives you dy dx. So this is important because what does this tell you? What is dy dx? That's the change in y over change in x, which is technically rise over run. And you know that this gives you the slope of the tangent line. dy dx is the slope of the tangent line. But dy dt, that's how fast y is changing with time. And you're going to see that's basically velocity in the y direction. And dx dt is how fast x is changing in the x direction. So that's the velocity in the x direction. G prime is dy dt because they are one and the same. And dx dt is f prime because they're one and the same. So this is how you find the slope of a tangent line. This is how you find the direction something's traveling. Because remember, parametrics, you have things moving. You have a start and an end, and it can be all different motions. But at any given time, you have a slope. And the slopes are different. And that represents the direction that they're traveling. So you will use this formula to get the slope of a tangent line or the directionality of your object where it's moving. So go ahead and pause and try this next example. Find the slope of the graph defined by x of t is t squared, y of t is cosine t when t is pi over 3. So if you were to graph this on your calculator, I don't know what it's going to look like. But an object's moving. So after pi over 3 seconds, what's the slope of the tangent line at that point? That's what we're doing. So welcome back from doing this problem. Hopefully you did it. I want the slope of the tangent line. It's dy dx. Well, I know that's y prime of t over x prime of t. So let's find that. X prime of t is going to be 2t. Y prime of t, derivative cosine, is opposite sine. So I'm just going to plug those in. And now, isn't this easy stuff? I want it when t, that's x, t is pi over 3. Well, let's plug that in. It's going to be minus sine of pi over 3 over 2 times pi over 3. And the sine of pi over 3 is radical 3 over 2. And this is 2 pi over 3. I'm going to multiply by the reciprocal. And I get an answer. Whoa, what just happened? This should be equals negative 3 radical 3 over 4 pi. There is the slope of a tangent line. So pretty easy finding dy dx for parametric curves. All right, now we're going to tie this all together. So we are doing multiple sections, but we're just going to do it all at once. Two-dimensional motion. So we have these things called vectors, and they're denoted with braces. See those angle braces? That's how we know we have vectors as opposed to a point or an ordered pair. So vector for position, well, x of t is the position in the x direction. Y of t is the position in the y direction. So that will be the position vector. Velocity vector. What's velocity? Well, the velocity is the derivative of the position, right? So the velocity vector, capital V for vector, I don't know if you notice that's capital V, it's going to be the velocity in the x direction and the velocity in the y direction as an ordered pair. A vector has two components, the velocity in x, velocity in y. Well, actually vectors could have more than two, but these have two. But how do you find velocity? It is the derivative of the position. So therefore, I get x prime and y prime from velocity vector. And then the acceleration vector, using the same principles from AB, the second derivative of the position is acceleration. The second derivative of position is acceleration. We just have two different directions, an x direction and a y direction. So we have acceleration in two separate directions separated out. So these are just concepts, and most of your FRQs are going to be based on these. So that's what's happening with these. And then speed. I think I need to spend some time on this so it will make some sense to all y'all. So what is speed in this case? Because speed in AB was the absolute value of velocity. But how do you absolute value this? That doesn't make sense. So I'm going to explain to you how we get speed and explain what this all means. Okay? So here we go. Here we go. Here we go. So vectors are represented by arrows. And suppose that's my velocity vector, x prime of t. And then I have a velocity in the y direction. Call that y prime of t. And the length of this vector is the magnitude. And so you can see the velocity in x is larger than velocity in y. And so in the x direction, the magnitude of that's pretty simple. We just put absolute value. That represents the length of it. So that's how long this vector is, and that's how long this vector is. Well, let me erase this now. So that's if you want the actual length, but this vector is represented by x prime and y prime, and to let you know it's a vector, we put an arrow to let you know it's a vector. But how do you add vectors? You did this in pre-calculus class, or you should have. So what's this vector plus this vector? You're going to take a hike. You're going to connect these vectors head to tail, head to tail. So take a hike down the x trail. That's x prime of t. And then you take a hike down the y trail, y prime of t. And you should have learned the sum of these two vectors is the one that connects the beginning to the end point. So you connect these together, and this is the sum of adding these two together. So how do you find speed? Well, it's a combination of two velocities. If you have a boat that's moving this way and it's moving that way, what's the resultant direction? Obviously, it's that way. How fast is it moving? Well, you take the velocity that way and the velocity that way. How do you figure out the velocity that way? It's Pythagorean Theorem. You take this velocity squared plus that velocity squared, and that gives you the magnitude of this. That is the resultant. This is the resultant of adding these two vectors together. So if you have a velocity in the x, a velocity in the y, what's the sum of those velocities? It's the hypotenuse. So therefore, the speed is the length of that side. And it's just a scalar. It's not a vector. So how do we find it? Pythagorean theorem, and you just get a number, no direction. Okay? So that's speed of an object. Are we ready to do problems? I think the rest of the way we're just going to be doing FRQs. 3 different FRQs to learn the application of vectors and parametric equations. 2012. All right, get ready. Here we go. Let's read. So t starts at 0 and gets bigger. The particle moves along a curve, so this is the position. And actually, I just realized this first one should not have been a vector. This is a position function. Position function, and it's not a vector. So if you plug in any two t's, you'll find the position of the object. But now the velocity is going to be a vector because you're going to get those quantities there. So that's the actual xy coordinate for the position. Just realize that. So here's your position given by that function. At time t equals 2, the position is 1 and 5. Now, we need to talk about this, and we need to tell ourselves what that means. That means that x of 2 is 1 and y of 2 is 5. It tells you when time t equals 2, I know the x and y position. Okay? Then we have dx dt and dy dt given. So we actually have the velocities in the x and y. So let's read part A. The horizontal movement of the particle to the left or to the right at times t equals 0. Oh, is the horizontal movement to left or right? What tells you movement left to right? It should be dx dt, right? The velocity in the x direction tells you left or right. So what we're going to do for part A, we need dx dt at t equals 2. And so plug that in. And this, by the way, is a calculator problem. So you just plug this into your calculator, but we don't need a calculator. This is easy. 2 plus 2 is 4. Square root of 4 is 2. So that's going to be 2 over e squared. That is a positive number. So the object's moving to the right. We need to state that. The object is moving to the right, but you need to give a reason. Why? Because dx dt at t equals 2 is greater than 0. So again, how does that fit with justifications? If the derivative is positive, then what is the derivative of is increasing. So since the derivative is positive, x is increasing. Well, if x is increasing, it's moving to the right. So that's what's going on for part A. Part B, find the x-coordinate of the particle's position at times t equals 4. Fundamental theorem of calculus. Let me remind you of something. Once upon a time, you learned the integral of x prime of t dt from A to B is x sub B minus x sub A. That's the fundamental theorem of calculus, used over and over and over and over in calculus. So x prime is velocity in x. So if I integrate the velocity, it gives me the change in position. So I'm going to use this, but look what we know. We want to find, oh, I didn't finish part A. I just realized that. I'm going to slide this down because I didn't finish part A. Part A had a second part. Find the slope of the path of the particle at times t equals 2. The slope of the path of the particle, hey, that is the slope of the tangent line. That's asking for dy dx, which is y prime of t. Okay, let me do some stuff because we want it at 2 seconds, right? So I should put t equals 2, which will be y prime at 2 over x prime at 2. And this is a calculator problem, so I can pop that in a calculator, plug in 2 here, 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 and clearly I need to do that with the calculator because I can't do that in my brain. And if you do in your calculator, you get 3.055. There's your answer for the slope of the path of the particle 2. Now let's do B. Let me slide this back up here again. So what do we have? We want the position's particle at t equals 4. We want x at 4. But notice we have x of 2. x2, x4. So we should use 2 and 4. And how's that going to work? To do that, we have to do this. We got to go from 2 to 4, and that's going to be 4 and 2. This I can pop in my calculator because I know x prime. I have that right here. So what else do I know? So I have the integral from 2 to 4 of x prime of t dt equals, and I know x sub 2 is 5, so it's x sub 4 minus 5. I'm going to add 5 to both sides, and here's what I get. X sub 4 equals 5 plus the integral 2 to 4 of x prime of t dt. Okay, I want to remind you how we learned this last year. This is the starting position. At 2 seconds, it's at 5. If you integrate x prime, it gives you the change in position. How much did the position change from 2 to 4? You add it to where it was at 2, and that gives you the position at 4. Now this, you pop in your calculator, and you get an answer. This will come out to be about 1.253. That's an approximation because we're rounding off, and that's the position at 4. Let's read C. Find the speed of the particle at t equals 4 and the acceleration vector at t equals 4. Well, we just learned the speed formula. Let me erase this so we can see what's going on. Delete. Delete, and do C here. Speed. The speed is that formula I just gave you. It is the Pythagorean theorem on the velocity at 4. So it's going to be v at 4, which is x prime. So I'll put x prime. X prime at 4 squared plus y prime at 4 squared. And now you just put in your calculator. Here's x prime, there's y prime. So that's just calculator work. You let the calculator do the work. And this comes out to be 0.575. And there's your answer for C. But we're not done. They want the acceleration vector. So the acceleration vector is going to be x double prime at 4 plus y double prime at 4. Well, again, your calculator does all this work, right? Your calculator will get you negative 0.041 and 0.989. Just pop that into your calculator. So that's part C. And then part D, distance traveled. Hey, that sounds familiar. That is arc length. That's what we did all the way up here. Arc length is the distance traveled. That's how long the curve is. So we're going to integrate this, part D. It's the integral, and it's from time 2 to 4. So that's the limits of my integration, 2 to 4. And it's going to be Pythagorean Theorem on delta x and delta y, which is x prime of t squared plus y prime of t squared dt. Well, again, this is calculator work. Just plug that into your calculator. We already have x prime and y prime. If you plug that in your calculator, it comes out to be about 0.651. Or if you truncate or round off, it comes out slightly differently. But that is how you do 2012 calculator FRQ on parametrics. Let's just keep going. 2015. At time t greater than 0, so again, we're given a time starts at 0, gets bigger. And here's the position x and y. And here's the velocity vector. That's my x prime, and this is my y prime. So I can conclude dx dt is cosine of t squared, and dy dt is e to the 0.5 t. So that's all the things I get. And then at t equals 1, that's the position. So what is that telling me? X sub 1 is 3, and y sub 1 is 5. So I'm pulling all this information out of this problem. So part A, they're focusing on the x-coordinate at times t equals 2. So I want x sub 2. Do I know where it started? I know x sub 1 is 3, so it's x sub 1. And I want to know how much the position's changed. To find the change in position, I integrate the derivative of the position, and I want to know how much it changed from 1 to 3, y 1 to 3. I know where it is at 1. Oh, it should be 2, not 3. y2, I want to know where it is after 2 minutes or seconds. I got no units here, 2 units of time. If I know where it is at 1, I want to know how far it moved from 1 to 2, and I combine those, and it tells me the position at 2. All right, again, this is just calculator work. Just punch this in your calculator to get the answer. These are things that you're allowed to use your calculator for. And if you work this out, it comes out to be about 2.557, and that would be rounded off. Okay? So that is part A. Let's do part B. Now we have a range of time from between 0 and 1. There's a point in the curve at which the line tangent of the curve has a slope of 2. So the line tangent has a slope of 2. What is the time? Well, how do I find the slope of the line tangent? That's dy dx, and I know that's y prime over x prime. What is that? Well, I know y prime and x prime. It's right there in there. dx dt, dy dt. So that's going to be e to the 0.5 t. Let me lower that. I'm getting scrunched. Oh, I picked up a 1 that I don't want. Over x prime, which is cosine of t squared. And that was given here. Now, they're saying, hey, there's a time when this slope equals 2. So I set that equal to 2. And how do I do this on the calculator? Very simply, I graph two functions. I graph that function as y1, this function is y2, and I find where they intersect. And I do that on the calculator, and you get t is If you find that intersection point on your calculator, you would get 0.840. And that's part B. Part C, find the time at which the speed of the particle is 3. Speed. Part C, what is speed? We just learned that. You're adding two vectors, you use Pythagorean theorem on the vectors. Speed will be x prime of t squared plus y prime of t squared square root. And they're asking, when will that be 3? Well, again, this is calculator work. You could graph this on your calculator, graph that on your calculator, and find where they intersect. If you were to do that, you would get a t of about 2.196 or 2.195 if you truncate. That's part C. Part D, find the total distance traveled. That's that formula we had earlier. You're going to integrate from 0 to 1, and it's Pythagorean theorem on delta x and delta y, which will be x prime of t squared plus y prime of t squared dt. Pop that in your calculator, you get 1.595 or 594 if you truncate. And that is another FRQ. Bammo. One more to go and this video's over. All right. A laser is a device that produces a beam of light. The design shown above is etched into a flat piece of metal using a moving laser. The position of the laser at time t is represented by this function. This is where the laser is pointing. Both x and y are measured in centimeters and t is in seconds. Centimeters and seconds. The laser starts at 0, 0. So we know the starting point is 0, 0. So in other words, x sub 0 is 0 and y sub 0 is 0. That's what this is telling me. And the design takes 3.1 seconds to complete. So t is going to range from 0 to 3.1 seconds. That's what I'm told here. That's that. And I guess I can color code this. That is that. Find the speed of the laser at times t equals 3. Again, that speed formula. The speed is going to be the Pythagorean theorem on the velocity vector. So it's going to be x prime at 3 squared, y prime at 3 squared. They gave me x prime and y prime, I think. Yeah, they did. Right here, x prime and y prime. Pop that in your calculator. So this, again, is a calculator question, and your calculator can do that wonderful work and get 3.065. So that's the answer. And if you want to write it out, you can say the speed of the laser at t equals 3 is 3.065 centimeters per second, because those are the units they gave us. All right, part B, find the total distance traveled. The distance is, I'm assuming it's going this way, it could be going the other way, and all the way back to the beginning. What's the total distance? That's arc length. Arc length. So the length or distance traveled is from 1 to 3, and it's going to be the Pythagorean theorem on that triangle, which is x prime of t squared plus y prime of t squared dt. And again, you just pop that in your calculator and you get 7.090. So we should write it out because we haven't really explained. So we should say the total distance traveled by the laser from t equals 0 to t equal 3 is 7.090 centimeters. Bammo. We are moving along. 2 more parts and we're done, and you guys will be ready to do your homework. Part C. The laser is farthest to the right at t equals 1.253 seconds. Find the x-coordinate of the laser's rightmost position. Wow. Check this out. I know the starting position. I want to know x at 1.253. So we're going to use the formula that we used all the time last year. That's the final position. I want the starting position plus the change in position. How do you find the change in x? You integrate x prime to get the change in x. And I want to go from 0 to 1.253 because that's my starting, that's my finishing, so I want to know how much it changed between those 2 points. Now you just pop this into your calculator again, and you get an answer. 2.932 approximately. So you could say the x-coordinate of the laser when it is furthest to the right is 2.932 centimeters. Done. All right, part D. What is the difference between the y-coordinate of the laser's highest position and lowest position? OMG. So let's interpret this. What is it really asking? What's the highest and lowest position? If you think about it, interpreting that is asking for the max and min of y. That's what it's really asking for. So how do we do that? Well, where do max and mins occur? You should know max and mins occur at critical points and endpoints. So we need dy dt, which is the derivative of the y, and set that equal to 0 and make it undefined. Where is that? 4 cosine 2.5t. So 4 cosine 2.5t. Now, a critical point is when a derivative is 0 or does not exist. This cosine always exists, so I set equal to 0. And on my calculator, I graph this, and I find where it crosses the x-axis, and I find all the numbers between 0 and 3.1 where that happens. And so I'm going to say that it happens at a equals, and on your calculator, you should find it happens at 0.628319, and b equals 1.884956. So these are the 2 places where this is true, and I find that on the calculator. All right, both of those are between 0 and 3.1, so we're mucho bueno. Now, where do max and mins occur? I'm going to remind you, if you have a continuous function on a closed interval, cosine's continuous, and this is a closed interval, we have the endpoints. So I'm going to give you different situations. And this is not the sign, it's just general function. If I draw this function, where's the max and min? At the endpoints. If I draw this function, where's the max and min? At the critical points. So max and mins could occur at critical points and endpoints. We don't know. So how do I know if the max occurs and min occurs here, or at the endpoints 0 and 3.1? How do I know? How do I know? Well, I want to find y at 0. I want to find y at the critical points, A, y at the critical point, B, and y at the endpoint, 3.1. How do I do that? I have a formula. I need to take the starting position of y and find the change in y. Well, this one I already found is 0 because they told us it's a 0. But I need to find the position at 0 plus the change in position, which is the integral of y prime. I got to scoot this over. And I want to integrate I need to, wait, first of all, let me get rid of these. Get rid of these, give myself some room. Then I'm going to take that and scoot it over, give myself lots of room. Right there, I like that. Okay, so you take the starting position and plus how much it changed, starting at 0, ending at A, because we want to know where it is at A. So we got to end at A. And this will be y of 0 plus the change from 0 to b of y prime of t dt. And the last one will be the starting position at 0 plus the change from 0 to b of y prime of t dt. All these are done in your calculator. If you pop those in your calculator, this is about 1.6, this is about negative 1.6, and this is about 1.591358. So, what the question asks, what's the difference between the highest and lowest position? Well, where's the highest? There's the highest. Where's the lowest? That's the lowest. Whoa, lowest. So I'm going to state the difference between the highest and lowest position is 1.6 minus negative 1.6, which is 3.2. I am El Dano. That is examples of parametric equations.